Hello students. In this video we're going to look at p-values, what they mean and how we can use them in hypothesis testing. First of all, as outlined in the course package, and maybe just a little different type of a brief explanation of p-values. P-values are the probability of obtaining the results. The results are from the sample data if the null hypothesis is true. Small p-values will lead to the decision to reject the null hypothesis, as the assumed value is not correct given the results of the observed sample data results. Because the sample data was observed, we are confident in making the decision to reject the null hypothesis. On the other hand, large p-values will lead to the do not reject the null hypothesis decision, as this is sufficient evidence that the difference between the observed sample data and the assumed value, the null hypothesis, is likely. So the key is how to differentiate between small p-values and large p-values. The key is the level of significance, or alpha. That is the determining factor. So we will reject the null hypothesis if the p-value is less than alpha. So now there's two ways to make our decision regarding any type of hypothesis test. This way, called the p-value approach, is looking at the p-value and comparing it to the given level of alpha. So let's look at some questions here. So question 1, the average income in Red Deer has been reported to be at least $80,000. A sample of 25 households is taken, which has revealed a sample average of $78,750. The population standard deviation is believed to be 2,500. Test the claim at 5% alpha and calculate the p-value. So what we're going to do with the first question is test the claim using both approaches. We're going to test the claim using the approach using the z-values, and then the approach using p-values. So we know that we're going to use a z-value in question 1 because we are given the population standard deviation. And this is a question dealing with the average. We have sample average, we have the population average, and we have the population standard deviation. So let's go to the whiteboard and list out what we know. Well, let's start with the null hypothesis. The null hypothesis is stated that the average is at least 80,000, and the alternate hypothesis is we're assuming that it is going to be, or we're testing to see if it's less than 80,000. We take a sample average came back to be 78,750. Sample size is 25, and the population standard deviation is given to us to be 2,500. And we are testing at the 5% level of significance. So the standard approach using these two z-values is first of all finding the critical value, z-alpha. Z-alpha is going to be based on 5%. It is a one-tailed test, so we're going to get a value. We can find it using the t-distribution chart. We're going to look at this column here, 5%, and there is our z-value, 1.64. It's going to be negative because we're dealing with values on the left side of the distribution. We're now calculating a test statistic. Test statistic formula is the sample mean minus the population mean over the standard error. Standard error is the standard deviation over the square root of the sample size. So this would equal 78,750 minus 80,000 divided by the standard deviation of 2,500 over the square root of 25. If you do that, we get a value of negative 2.5. Our decision rule when doing the approach using the two z-values is to reject the null hypotheses if the test statistic, this value, is greater than the critical value. So remember that when you're making that decision, to treat each of those values as positive numbers. So in this situation, we will make this decision. We will reject the null hypotheses. We have enough evidence to go back to the City Council and say that the average income is not 80,000. So now let's take a look at how to do this using the p-value approach. Let's get some more room here. P-value approach, we start off with the null hypotheses. It is it is the same. That's assumed to be true, that the average is greater than 80,000. We're testing to see if it's less than 80,000. We have the same sample data. The key is the level of significance, alpha, being 5%. And that it is a one-tailed test. We know it's a one-tailed test because of these signs in there, the greater than and less than signs in the null and alternate hypotheses. So the test statistic is something we still have to calculate. The test statistic turned out to be negative 2.5 based on the work we've done previously. What we want to do here is this follows the three-step approach we took in chapter 6 to find the probability or the area of a value being greater than or less than a certain point on that normal distribution. So this would be step 1, calculate Z. Step 2 is to find the area. The area that corresponds to a Z value of 2.5 is right here. 2.50, the first column is 0, so 4938. So let's put that in there, 4938. The last step is the p-value. The p-value calculation is always taking that area, subtracting it from 0.5. So we will get a p-value of 0.0062. We can make our same decision to reject the null hypotheses as we did previously, but instead of using the standard approach, using 2Z values, we can use the p-value approach. So our decision rule, let's put that up here, is to reject the null hypotheses if the p-value is less than alpha. Let's go with green. There's alpha, and there's our p-value. So the p-value is 0.0062. This corresponds to approximately 0.62% chance. So that means that there's way less than 1% chance of the observed difference occurring in the world in terms of they believe that the average is 80,000. We took a sample and found that sample average to be 78,500. That difference should not happen. So something is wrong with the assumed value. You have to remember that the null hypothesis is an assumed value, and we're testing against that assumption. So we have enough evidence to say that that observed difference should not happen. Our p-value is, let's look at this one here, 0.0062 is less than 0.05 for our level of significance. We'll look at the other questions. Question 2, the average income in Red Deer has been reported to be equal to 80,000. The population standard deviation is given, so the question is the same. The only difference is that we have that change. So we are, in question 2, dealing with a two-tailed hypothesis test. Let's go here, let's erase this. Two-tailed hypothesis test is going to look like this. The average equals 80,000. We're testing to see if the average is different than 80,000. So everything else stays the same. The test statistic is still going to be negative 2.5. That does not change if it's a one-tailed or two-tailed test. The formula is the same. The values in that formula have remained the same. So everything in the question has remained the same. Even the area that corresponds to that Z value of 2.5 stays the same. It's still 4938. 4938. The p-value still calculated the same way. 4938. So this equals 0062. But because it is a two-tailed test, and we know that from those equations in the null and alternative hypotheses, what we have to do with the p-value is multiply it by 2 because it's a two-tailed test. So the p-value will equal 0.0124, or this is the same as a 1.24% probability of occurring. Given that, which would mean that given the assumed value is 80,000, the probability of that value being true given our data in our sample is really small. It's 1.24% chance of occurring. Because it is still less than alpha, alpha hasn't changed, alpha is 0.05, we are going to make this decision to reject the null hypotheses. Because the p-value, right here, is less than alpha value. What I would recommend doing if you want to see the other approach is doing question 2 using the two Z values. You're going to have the same test statistic of 2.5, but you'll have a slightly different critical value because it is a two-tailed test. We'll look at question 3 and 4 in the other video.